Okay, so how do we interpolate data in more than one dimension? So let's just assume for a second we have a grid. Let's call it xi, yi in R squared. That's the real plane, right? Where I is equal to 0, 1, 2, right? So we have a list of function values that we want to interpolate. That's going to be f xi, yi, right? And so we're going to plot these on the z-axis, and those are kind of like our blue dots on the right, with the red dotted line being the height of those lines on the z-axis. So what we want is we want to come up with a list of basis functions, like we did for the one-dimensional case, where we're equal to 1 at the coordinate, and we're equal to 0 at any other coordinate. So we're equal to 1 at our reference coordinate, so let's write that out. So we want to create a function, L that is equal to 1 when just xy is equal to xi, yi. Or rather, I should probably say xj, right? Because we're not always at the same coordinate, right? We want to kind of be better about that, right? J. Let's make that better. There, right? Xi, yj. When we're at the location, and then 0 at all other nodes. Right, and that's going to be, right, so we don't just want one of these functions. We have, this is indexed ij. Okay, so how can we do this? The way that, and this is going to sound kind of strange at first, but the thing that I'm going to say right off the bat is that 1 is equal to 1 times 1. Hopefully, that's okay with everyone. So we're going to actually use this idea, this pretty hopefully self-explanatory idea that I just wrote down, to make these polynomials. So I'm going to create a polynomial. Oh, by the way, this is what the basis functions that we want them to look like. So at some point, we want z to equal 1, right, where this is L. Right, this is our L. We want z to equal 1, and it's going to be 0 everywhere else. So there's that. So let's keep this up here for reference later on. Okay, so let's take this idea and let's move it down here. So I'm going to create one function that's x, and I'm going to create another one that deals with y. And that way, when they both are satisfying the xi, yj condition, we multiply them together and we just get 1. So what I'm going to call the first one, let's call it Lx, x, and we're going to have Ly of y. Okay, and but we need Ly at P. So we have to have some point P that we're referencing. This is similar to saying xij, yij. This is going to be that's sort of same idea. So let's develop this. So like last time, I'm going to say that Lxp of x is going to be the sum of, let's see, we have, and now we don't, I never actually specified how many points we have. So what I'm actually going to say is just all of them. So from n equals 0, n not equal to p, up to capital N, the number of points, right, in the x direction, we have x minus xn over xp minus xn, right? So this should look familiar. This is exactly the same thing that we did last time. But now let's just create the identical, the exact same function, but for y. So we're going to have Lyp, y. and this is going to equal the pi notation, the product. But now we're actually going to have another, we don't necessarily have the same number of points in x and y, so we could actually be in a rectangle. So we'll go from lowercase m equals 0, m not equal to p, and then we'll have x minus x m, nope, but it's y, right? Y minus ym over yp minus ym, right? And that's going to be our function there. So yeah, like I said, these are both equal to 1 when the function is at the correct x or y location. So, right, if we're not multiplying these together, we can see that if we're at the xp point, then we'll be equal to 1, and if we are at some other node, then we will not be then we will be equal to 0. Yeah. Okay. So, like I said, 1 times 1 is equal to 1, so we actually need to multiply these together. So I'm going to say that Lij will be equal to Lxp x times Lyp x, and then let's write out exactly what this is. So we're going to have the Lx n not equal to I, x minus xn, x, and then we have x, right, x I minus xn, right, times the other one. So the y version of this, m not equal to j, right, because now we're talking about that one, y minus y m minus yi minus ym. Okay, and there we have it. So let's check for some point, let's check if our interpolation condition is satisfied. So let's just take a look at this. So let's say for I equals 2 and j equals 3. Let's check this. So right, we need to plug this in. So we have L23 is going to equal this, n equals 0, n not equal to I of x minus, and now xn is just still a variable inside of this product notation, and then our xi is actually x2 minus xn, and then we multiply by this one, m equals 0, m not equal to j of y minus ym over y3 minus ym. And so now this is going to be our basis polynomial. So now we're going to plug in xi yj equal to x2 y3. So let's do that. We're going to have, right, so L23 at x2 y3 will equal, all right, I'm being careful with the notation here. We'll have x2 minus xn over x2 minus xn. So that's equal to 1, right? And then we'll multiply by this one, m equals 0, m not equal to j, and then likewise we have y3 minus ym over y3 minus ym, right? And so then this is equal to 1, right? So now we have to check, okay, does it equal 0 everywhere else? And that's going to be a more complicated answer, but what's going to happen is, right, I never specified how many n and m there are. So what would happen is at some point in the expansion, if we expanded, we got rid of the product notation, we would have x2 minus x2, because xm, right? So for xm would equal x2 when m is equal to 2. And that's how we would show that this is equal to 0 at any other point. So, well, this wouldn't happen at this point, but this would happen at one of the other points. So say at x equals 1, we would have x equals 1, and if we were equal to x equals 1, we would subtract x equals 1, and we would have 0 over some number. And then we would be satisfying the interpolation condition in that way. Okay, so we have shown, hopefully satisfactorily shown, that this L function is equal to 1 exactly at any grid point in our rectangular grid. So let's put a nice box around, not that one, this one, right? This is a nice function. We don't want this one. So let's copy this guy and let's work with this on the next page. Okay, so this is what we had. This was our L function, right? This was L, I, J, right? And so now we want to say, okay, if I'm at the function value, right? If I'm at xi, yj, right? I just need to scale by my function value. So we're going to say that at some point, xi, yj need to equal f xi yj. Well, good news. We just need to multiply by 1, right? So what we're going to do is we're going to take each one of these and we're going to multiply it by its corresponding function value. So let's create some room to talk about that. So what is that going to look like? All right, so we are actually going to have a double summation here. And this is going to look fancy, but I promise that it is going to make sense. I can't promise you that, but I can promise that the notation is going to be right. So we're going to create a polynomial Pnm. All right, so this is going to be m degree, a capital M, capital N by m, right? So depending on the number of points we have, this will have that degree of, it'll actually have n plus 1, m plus 1 degree polynomial, but it's not exactly important here. I'm just kind of using this to show that we have 2 dimensions in our polynomial and they might be different. So we're going to have the sum of all of the m's and n's. And we're going to have L, M, N and we need to do that, yes, we need to do that, of xy times f xn and ym. And there we go. That is going to be the polynomial that is going to interpolate our 2-dimensional data. And so that's going to be our general form. So now stay tuned for a quick example. Okay, so with this formula in mind, let's do an example, because an example is going to kind of show that this is what's happening, and it's going to make a lot more sense, I think, if we dumb it down to the nuts and bolts here. So I'm going to say for this set, the Cartesian product of 0, 1, and 0, 1. If you don't know what that is, that's basically we're just going to create a grid like this. Right, we have 0, 1. Right, well, this is 1, 1. This is 1, 0. This is the origin, and this is what is it, 0, 1. Yeah. Okay, yeah, so this is our grid. These are going to be our xi, yi points. And so we're going to create a one-dimensional, or a degree 1 polynomial. So this is actually going to be, this will be a quadratic surface. So let's use the formula now to create the function values. But actually, we have to create, like I said, some function values. So I'm going to say this function is going to be equal to 1 at 0, 0. It's going to be equal to 2 at 1, 0. It's going to be equal to 3 at 0, 1, and equal to 4 at 1, 1. Right? So this is going to be the f of xm, ym data. Okay, so now we have everything we need. We can just plug this into our formula. So let's see what we've got. So we've got p 2, 2. All right, I said it was m, but it's actually going to be n plus 1, m plus 1, if we want to talk about the degree in each direction. So this is going to be equal to the sum over both of them. There's only one, and so this is a very compact way to write this. And so we will have n m x y f x n y m. Okay, so this is going to be a very large thing to write out in one line, but let's do it. So we're going to start by taking the 1 value, and we're going to multiply it by the correct point. So we said at 0, 0 we were equal to 1. So that means we're going to take x minus 1, right, the point that we're not at, y minus 1, the other point that we are not at, right? Because that's what, right, x1, I should probably specify, right, x1 is equal, x0 is equal to 0, x1 is equal to 1, y1 is equal to 0, and y0 is equal to 0, and y1 is equal to 1. So we're going to put those directly into the formula because, right, we can't actually get an answer without defining exactly what the numbers are. So, right, but then we at the point 0, 0, we want this to equal 1. So when x is 0 and y is 0, we have -1 and -1, so we have to have 0 minus 1, and then 0 minus 1. And that makes sense, right, because our point was 0, 0. Like I said, x 0, y 0. Okay, so that's good. And then we have to add on the 2, right? The function value was 2. This is f of, what is it? F of x1, 0, right? So x is 1, so now we're going to have x minus 0, right? The point that we're not at. And then y minus 1, right? And then when we are at 1, 0, we need this to equal 1. And so what do we have? We have the same thing as before. No, we have, right, when we were at 1, 0, we need to have 1 minus 0, and then y is 0, so we have 0 minus 1. So now we can look at this quick and we can say, okay, at the point 1, 0, I plug in 1 for x, I get 1 in that spot. I plug in 0 for y, I get minus 1. Now I have 1 times minus 1 over 1 times minus 1, and that will make sure that my function is equal to 2 at that point. And then at the same time, while we're looking at this, we can go back and say, okay, at the point 1, 0, I'm equal to 0 because of this, right? And so you might ask, like, oh, there's 0 over 0, but because this, or no, we're fine in that department, right? So we're still satisfying the interpolating condition, okay? And then we have the 3 part, right? The function value is equal to 3 at 0, 1, so we'll have x minus 1 and y minus 0, right? We haven't had y minus 0 yet. And then we're at the point 0, 1, so we have 0 minus 1 and 1 minus 0. And then again, we ask ourselves, does that equal 1 at the point 0, 1? So at the point 0, 1 in the numerator, I have negative 1 times positive 1. And on the bottom, I have negative 1 times positive 1. So that means I'm equal to 1. And then let's see if we can fit this all on one thing. No, we can't. We're going to have to put it down here, right? Plus 4. The condition at 4 was that we were at 1, 1, so we need to have x minus 0, y minus 0 over, and then we need to be equal to 1 at the point 1, 1. So we need to be, we need to have 1 minus 0 and 1 minus 0. And then again, we ask ourselves, are we equal to 1 at the point 1, 1? At the numerator, we have 1 times 1, and the denominator, we have 1 times 1. Okay, so this is the example, right? This is going to create a quadratic surface for us that's going to interpolate between these 4 points. I'll skip the algebra because it's kind of annoying to do because I wrote minus 0 everywhere, which can be kind of annoying. What it ends up coming out to is 4xy minus 2x y minus 1 minus 3 times x minus 1 y plus x minus 1 minus 1. And then this should make even more sense now that we have this going on. We can see that at the point 1, 1, we're equal to 4. At the point 0, 0, we're equal to 1, right? So I wrote it like this so that we could see that this is the condensed form of what we have up top. So this is going to be the answer to our example. And now let's actually head over to GeoGebra and see if this is correct. So turns out I lied. This is a linear surface. We are not looking at a quadratic surface. I should have known that because there's no point where we have an x squared or a y squared. But as you can see, we have our 3 points here. Let's look at it from the top. We clearly have 0, 1. We have our grid that I drew out before. And we have a surface that passes through these 3 points. It's not very glamorous, but as you can probably assume, we could expand this to as many points as we want, and we would get the same result, that this surface would interpolate these 4 points, or as many points as we wanted, right? This can be rectangular, this can be a square. Still working on the triangle method at the moment. I'm not, that was a lie. But yeah, now there we have it. Let's go back to our thing here, and yeah, so let's correct that, right? This was a linear polynomial, so we're actually looking at 1, 1 here. But yeah, there you have it. This is going to be your formula for creating a higher dimensional polynomial interpolating surface. Have a nice day.